Now we will move into the next topic, that is a distribution function. That is distribution function. This is nothing to do with probability. So, first let me define the distribution function, then we will connect the distribution function with the probability. Therefore, the same distribution function will be called it as a cumulative distribution function of a random variable x. So, when I define now the distribution function, there is no probability at all. Okay. Let me define a distribution function. Definition: a real valued function capital F, because later we are going to use this capital F as a CDF. Therefore, I am going to use now itself capital F. A real valued function capital F satisfying 4 conditions. The first condition, it is always lies between 0 to 1. For all x lies between minus infinity to infinity. This is the first condition. Second condition, it is a monotonically increasing function in x. That means, if two values you take x1, x2, x1 is less than x2, then the f of x1 is always less than or equal to f of x2. It is same as a non-decreasing function. Either you say it as a monotonically increasing function for two different values of x1 less than x2, then f of x1 is less than or equal to f of x2, or non-decreasing function, both are one and the same. Third condition, limit x tends to minus infinity of f of x, that is 0, as well as limit x tends to plus infinity of f of x is 1. It is not substituting the f at minus infinity is 0, f at plus infinity is 1. It may holds in some examples, but the definition is a limit of x tends to minus infinity, that has to be 0, limit of plus infinity, that has to be 1. It is not a substitution, it is a limit. The fourth condition, that is the capital F is a right continuous function. I can use the word, I can write right in the bracket. That means the function can be continuous, if not it is a right continuous. The function is continuous function, if not it has to be a right continuous function. If these 4 conditions are satisfied, then you can conclude the f is a distribution function. Then the function, the real valued function capital F, that is called a distribution function. As I said, this is nothing to do with the probability. Any real valued function satisfying these 4 conditions is going to be called it as a distribution function. If even any one of the properties are not satisfied, then you cannot conclude. It has to be a real valued function, value lies between 0 to 1, it should be a monotonically increasing, limit value has to start from 0 at minus infinity and it had to end up 1 as a limit extends to plus infinity, and either it should be a continuous or a right continuous. You can draw some diagram for the function capital F and you can get the feel. After that we can introduce the probability, then we land up a cumulative distribution function of the random variable x. So, let me start what are all the graph of capital F, so that that is going to be the distribution function. You can also try to draw the graph, x axis x, y axis is capital F, so that satisfying these 4 conditions, therefore that is a distribution function. You try, I will also going to give some 2-3 diagrams, so that you can conclude which one is going to be distribution function, which is not a distribution function, and so on. Examples. First example, when I ask the students to draw the diagram, they can make it a different type, whether it is going to satisfy that 4 condition or not, that is important. Since its value is from 0 to 1, the easiest diagram, the values is 0 till this point, and this point it increases, becomes 1. Therefore, this satisfies all the 4 conditions, therefore it is a distribution function. I can put the tick mark here. I draw another diagram. At some point it has an increment. So, this point you treat it as -3. At some other point it is not scaled. Okay. At some point it increased. At some other point again it increased. And this value, suppose that is going to be 1. Suppose this value is going to be 1. That means till -3 it is 0. -3 to 4 it has some value constant. There is an increment at the point 4, and between interval 4 to 10 it has the same value. At the point 10 it becomes 1, and it is 1 till the end. Therefore, this also satisfies. I will go for another diagram. As a third example, it is 0 and it is increasing, and it is touches, it becomes 1 at infinity. That means asymptotically it goes and it becomes 1 at infinity. So, see the difference of the 3 different distribution function. The first one has only one jump at the point 1. The second one has 1, 2, 3 jumps, and the third example which does not have any discontinuity or no jumps. It starts from 0 and it goes to 1 and it is a continuous function, whereas the first and second example are the right continuous function. That means the way I define the value at the point wherever there is a jump and what the value at the right limit are same, which is different from the left limit in the first two examples, whereas in the third example it is a continuous function. Or I can go for one more diagram. It takes a value 0 and it is increased to some value. At some point there is a jump. At some point there is a jump, then it becomes 1. That means it is continuous between the interval minus infinity to, suppose this point is 20. This function is continuous between the interval minus infinity to 20. 20 there is a jump and it becomes 1 from 20 to infinity. Therefore, it has a continuous in some interval, jump at one point, or there is a possibility it may have a jumps at many points. It may have a combination of continuous in some interval as well as jumps. Whereas if you see the first example and second example, the distribution function increases the values only by jumps. I am repeating the word. The first example and the second example, the distribution function start from 0, it incremented at some value and it becomes the same value till the next jump. Then the next jump it increases till the next jump, then it again increase, then it goes to the same value. Therefore, the value increases only by jumps in the first example and the second example, whereas in the third example it increases continuously from one point till the end, whereas in the fourth example it increases in some interval as well as it is retained the same value with some jumps. Therefore, all four types are going to be the distribution function. I have not given what is a function which is not the distribution function. So, you can think of a wrong example of increase decreasing or not values or lies between 0 to 1, it more than 1 or less than 0, or it is discontinuities. So, violating these four conditions, you can always create n number of examples which are going to be a non-distribution function. But what we want is a real valued function satisfying the four conditions. Therefore, this is going to be a distribution function. So, this four example makes the first example has only one jump, the second example has 3 jumps, like that you can have a finite number of jumps. The third example does not have a jump at all, it is increasing in the whole interval, and the fourth example is a combination of increasing as well as having a jumps. We can go for one more example which has the countably infinite jumps. That makes a completeness of the distribution function. So, the fifth example is having a countably infinite jumps. Countably infinite jumps. So, it starts from 0 and it has a jump, again it has a jump, again it has a jump, again it has a jump. Like this it is keep going, it reaches 1 at some point. The first example has only 1 jump, second example has 3 jumps, fifth example has a countably infinite number of jumps, third example does not have a jump, fifth example has a 1 jump as well as increasing between the sum interval. This shows the distribution function can be of many form. So, this will lead us to create types of random variable in the later stage. But before that, let me explain what is a cumulative distribution function through the distribution function. That is going to be the next definition is a cumulative. Next definition is cumulative distribution function of a random variable x. So, this is CDF is denoted by capital F suffix x, that is denoted by capital F suffix x. That is a cumulative distribution function, and how it is defined for all x, that is same as P of x is less than or equal to small x, where small x is in the real line. The capital F which we define, that is a distribution function. Extra we are using a suffix capital X, that is to show that the same distribution function capital F is call it as a cumulative distribution function of a random variable x. So, whether I write a capital F suffix x or capital F of x, both are one and the same. So, I can use a word or here to distinguish or to tell that both are distribution function, and the way you define the distribution function through the P, that P comes from the probability space omega f p. The same capital P is used. In the probability space you have a capital P, that is a probability measure set function. So, if you find out P of x is less than or equal to x for all x belonging to R, this way if you define the distribution function, and that distribution function is going to be called it as a cumulative distribution function of a random variable x. Now, the way we write capital P x is less than or equal to x, the way you define this way, the distribution function is going to be called it as a cumulative distribution function of a random variable x. In short, they use CDF. CDF means a cumulative distribution function. I can expand what is the meaning of capital P less than or equal to x. That means that is same as capital P of the capital X less than or equal to x is nothing but for possible outcomes W belonging to omega such that under the operation x, the W gives the values x of W gives the values less than or equal to x. That is the meaning of capital P x less than or equal to x. Means you are collecting few possible outcomes which satisfies the condition x of w less than or equal to x. This is nothing but a set. This is nothing but an event. The way I explained in the earlier, this can be denoted by the letter called a suffix x. That means it is a p of event a suffix x. A suffix x as an event. This event is belonging to the f. By using a Kolmogorov axiomatic definition, the p of a suffix x gives the values greater than or equal to 0 for all events, and p of omega is equal to 1, and p of union of mutually disjoint events, that is same as sum of p of a's. Using the same Kolmogorov axiomatic condition, the capital F is defined for all x belonging to real line. That means when x between minus infinity to plus infinity, you will get the values of p of x less than or equal to x. That will satisfy the 4 condition which we said it earlier. That is, it's a real valued function, lies between 0 to 1, monotonically increasing, limit is minus infinity 0, plus infinity is 1, and f is a right continuous function. So, all these 4 conditions will be satisfied. Therefore, this distribution function, the capital F, that is going to be called it as a cumulative distribution function of the random variable x. That is denoted by capital F or capital F suffix x. When we have more than one random variable, the suffix is important. Now we have only one random variable, therefore whether you write f of x or f suffix x, both are one and the same. Now let us prove how this function capital F x is going to be the distribution function. Once you prove that it is a distribution function through the p x is less than or equal to x, then you can conclude the same distribution function is going to be called as a cumulative distribution function of the random variable x. Even though there are 4 points to be proved, the first one is lies between 0 to 1, and the second one is monotonically increasing or non-decreasing function, and the limit is minus infinity 0 and plus infinity is 1, and right continuous. So, we will prove only few things, the remaining proof can be done it in the similar way. The first one, to prove that it is non-decreasing or monotonically increasing, you take 2 points with x1 is less than x2, and you can always conclude minus infinity to x1, which is contained in minus infinity to x2. This is a one set, and it is another set, and the one set is contained in the other set. Suppose you go for finding what is a f of x1, that is nothing but the p of x is less than or equal to x1. That is same as p of set of all w's belonging to omega, such that x of w is lies between minus infinity to x1. Since one set is contained in the other set, or equivalent of one event is contained in the other event, then the probability is going to be less than or equal to. Therefore, that is less than or equal to the p of collection of w's, such that minus infinity to x of w is less than or equal to x2. This is nothing but p P of x is less than or equal to x2, and that is same as f of x2. Therefore, we can conclude f is the non-decreasing in x or monotonically increasing. The second one, we can prove limit x tends to minus infinity of f of x is 0. For that, we take sequence xn be a sequence of real numbers such that it is decreasing to minus infinity. Then you can conclude x less than or equal to small xn, that is satisfies this condition. For each n, not only that, the limit n tends to infinity, the event x less than or equal to xn, that is nothing but intersection of x less than or equal to xn, where n goes from 1 to infinity. Since xn's are the sequence of numbers decreasing to minus infinity, satisfying this condition, therefore, limit n tends to infinity x is less than or equal to xn is same as intersection of x is less than or equal to xn, where n running from 1 to infinity. That is nothing but the empty set. That is nothing but empty set. Therefore, limit x tends to minus infinity of f of x is same as limit n tends to infinity of p of x is less than or equal to xn. Just now we concluded limit n tends to infinity x is less than or equal to xn is empty set. Therefore, this is nothing but p of I can interchange the role of limit and probability, because p is a continuous function. P limit n tends to infinity of x is less than or equal to xn, and that is empty set. So, the p of empty set is going to be 0. So, we have proved limit x tends to minus infinity f of x, that is going to be 0. Similarly, one can prove limit x tends to plus infinity of f of x, that is going to be 1. And fourth one, one can prove the f of x is the right continuous in x. So, since all the 4 conditions are satisfied for the distribution function, therefore, this distribution function capital F is called the CDF of the random variable x. So, the distribution function satisfying p of x is less than or equal to x form, that distribution function will be the cumulative distribution function for the random variable x.